Okay, so we'll get started since it is already 6:30. So hello everyone to the week 7's TA session of the course, Optical Spectroscopy and Microscopy, Fundamentals of Optical Measurements and Instrumentation. Um, so the plan for this TA session will be simple. So where we'll be going through a brief recap of the uh, contents of the course taught in week 7, followed by which we'll be discussing some of the previous sample problems along with some of the problems that I have curated for this week to help you to go ahead with solving questions in the exam. So can't see anyone in this room right now, so I'll get started right away with. Yeah. So, uh, week 7's, uh, we are halfway through the course, and where we initially started by discussing about quantum mechanical principles of light, how light can behave in different states of matter, as well as how the process of absorption and fluorescence happens. It was explained through quantum mechanical principles. Following which, in last week, we started discussing about the applications of light, especially in lasers, which will be used to make optical equipment such as your microscope. So when we are discussing about microscopes, we were discussing about the different technologies that will be used to develop microscopes, and depending on the resolution that we want to be used. In that aspect, we were discussing about last week. We were discussing started to discuss about continuous wave lasers, where we discussed about the process of continuous wave process in which continuously wave lasers work, and how we discussed about 2 level, 3 level, as well as 4 level lasers, and how we discussed about each of their efficiencies along with certain parameters such as coherence as well as spectral brightness. So week 7's course content is a continuation of your week 6's course, where we are starting to talk about your pulse wave lasers. And initially, we started by discussing how a pulse wave laser is different to a continuous wave laser, where we can see that although the average power for the pulse laser is comparable to that of your continuous laser, the peak power of the pulse laser is many times higher that of the continuous laser. And so pulse laser is a type of laser where you get your laser output in form of pulses rather than as a single continuous form in the case of your continuous laser. So as a result, your average power may be comparable to your continuous wave lasers, but your peak power for the pulse laser in your will be much more higher, giving you a lot of energy in a short amount of time. And pulse laser can be differentiated into um, several types of lasers depending on their pulse width, mainly your nanosecond laser as well as your picosecond or your femtosecond laser, where the pulse width keeps reducing in the terms of 10 power minus 9 to 10 power minus 12 or 10 power minus 12 seconds. And the advantage that we saw in the week's lectures from continuous wave to your picosecond or femtosecond laser is your uh, accuracy of your lasing medium onto your target. So as we move on from continuous wave laser to a nanosecond laser to a picosecond laser, our accuracy of our laser increases, uh, by means of which you will be um, targeting only the specific area of lasing that you want in the end. So at the start of the week 7, we saw about basic uh, beam profiles, how light wave reacts with respect to the distance, how it is diffuse in nature, and how as the distance increases from a object, the intensity reduces exponentially. And we also saw certain parameters about your beam waist, as well as we saw how pulse wave lasers work, and we saw how in a specific lasing cavity where you have a lasing media with two mirrors, the laser can be activated only in different modes. These modes are actually frequencies at which the laser can operate, and these will be in multiples of the specific mu naught, which will be uh, which we can compute by using the length of the lasing medium. So it will depend on your speed of the light as well as your length of the lasing medium, which we'll cover. You would have seen about the expression, this particular expression, del mu is equal to c by 2l, where l is your length of the laser. So using that, we'll be able to calculate which orders of magnitude of specific frequency the pulse wave laser will happen. And under the pulse laser, we saw several ways by which a pulse laser can achieve population inversion. Two of which was Q switching as well as mode locking. So initially, when we started about Q switching, we saw about Q factor, which is the loss coefficient. So the Q switching process was mainly involved in reducing this loss, by which we were using this Pockels cell, which is a electro-optical device that can modulate your birefringence. So we saw how the combination of Pockels cell and your polarizer functions as a shutter for the laser, through which you will be able to produce your pulse laser. And after the process of discussing about your Q switching, we also saw about a process called mode locking, where we saw what mode locking actually means. So basically, like I said before, in your in your bandwidth of the bandwidth of the laser, you will have certain um, your laser operating at different frequencies. So all the frequencies, if it operates at the same phase without any phase differences, that process is called as mode locking. So we saw how mode locking like we got a brief introduction to how mode locking happens as well. So that was about the contents of week 7, and the session is now open for doubts. So if there are any doubts, you can shoot it up now before we start to discuss the problems for week 7. Okay, then, if no one has any doubts, I'll get started with the problems. So, first question, which technique is primarily used to transition from nanosecond laser pulses to femtosecond or picosecond pulses by synchronizing cavity modes? So, the options are Q switching, mode locking, spontaneous emission, and polarization anisotropy. So, just look like the keyword here is synchronizing cavity modes. So, as soon as you can hear the synchronization, you can say that the option would be like it would be something associated with mode locking. Just a second, I just check if it's recording. Yeah, mode locking. The second question, the frequency spacing delta nu between adjacent longitudinal modes in adjacent longitudinal modes in a laser cavity of length L is defined by the formula. This we already discussed in the course recap as well as in the course contents. Uh, it's defined by the formula delta nu is equal to c by 2 lambda, where c is your speed of light and L is your uh, cavity of the length of the laser cavity. So, question number three. According to the uncertainty principle, what must be done to the spectral bandwidth in the frequency domain to generate a shorter lace pulse in the time domain? So, according to the uncertainty principle, what must be done to the spectral bandwidth in the frequency domain to generate a shorter lace pulse in the time domain? So, we all know that for the mode locking to happen, you need a lot of pulses in the lot of harmonics of the pulses to be synchronized. So that would involve a larger bandwidth. So the answer would be bandwidth must be increased. Question number four. What is the specific role of a acousto-optic modulator when placed inside a laser cavity for mode locking? What is the specific role of an acousto-optic modulator? So in octo modulator, know that it acts as a switch to ensure that all the frequencies start in phase. Question number five: what is the physical consequence of phase locking multiple longitudinal modes inside a cavity? So what is the physical consequence of phase locking multiple longitudinal modes in a cavity? So the options here are the modes interfere destructively, leading to zero output. Option B, the modes produce a continuous, non-fluctuating wave. Option C, the modes undergo constructive superposition, creating a constructed pulse train. Option D is the modes shift their frequencies to a single central value. And the correct option here is the modes undergo constructive superposition, creating a constructed pulse train. So you all know that phase locking is intended to lock all the phases together, so leading to a increased frequency. So the frequency increases, the time resulting time decreases, and superposition is the main idea behind your getting your phase locking and your pulse laser, getting pulse laser of lower pulse width. So this is a repetition of your second question. So to achieve effective mode locking, the modulation frequency omega of the internal modulator must be matched to what? And we all know that if it's a frequency and if it's to be mode locked, so it should the modulation frequency omega should be matched to the longitudinal mode spacing, which is given by C by 2L. Question number 7. Ultra-short pulses produced by mode-locked lasers are a critical requirement for which advanced imaging technique? So, we are ultra-short pulses produced by mode-locked lasers are a critical requirement for which advanced imaging technique? So, if we go over all the options here, we have the basic absorption as well as fluorescence spectroscopy here, which do not need very ultra short pulses. In fact, even using continuous lasers, the process will work. So those are not the correct answers. And light scatter counting also requires a continuous laser. So the only option here which requires a pulse laser is multiphoton microscopy. So that's the correct option. Question number 8. The specific frequencies sustained as longitudinal modes in laser cavity are primarily determined by what? So they are asking the specific frequencies sustained as longitudinal modes in a laser cavity are primarily determined by length, temperature, diameter, and sensitivity. So we all know if it's a frequency in longitudinal mode locking, it's primarily determined by the length. So the answer is option A, the length of the laser cavity, L. So we'll go to the problems next. These are all the theoretical questions. So calculate the energy of a single light photon with a wavelength of 1240 nanometer. So it's a very straightforward question. So we are just given the wavelength and we have given you the Planck's constant in electron volt and the speed of light. So you just need to substitute the formula E is equal to hc by lambda and plug in the values for h, c and lambda in their respective units. So as a result of that, you will get your energy as 1 electron volt. The last and the last question. Research grade laser has a cavity length of 1.5 meter. Calculate the frequency separation in megahertz between adjacent longitudinal modes sustained within this cavity. So they're given the length, cavity length, that is 1.5 meter. We have to calculate the frequency separation between adjacent modes. So we know that the frequency separation, which is given by del mu, is given by c by 2l, which is uh, so where c is your speed of the light, which is the 3 into 10 power 8, and l is your cavity length, which is 1.5 meter. So you just substitute the values of c and l in this formula, where you get your delta mu as 1 into 10 power 8 hertz, but they are asking the answer in megahertz. So we know that 1 megahertz is 10 power 6, 10 power 6 hertz. So we'll eventually get this as 100 into 10 power 6 hertz, which is 100 megahertz. I hope the questions are clear. If not, um we'll have one more doubt session before we start discussing the next set of problems, which is the week 5, half of the second half of the week 5. So the last week we discussed week 4 and half of week 5's problems. So in this week we'll discuss the remaining half of week 5's problems. We'll start with discussing the remaining half of week 5's problems, and we'll discuss the week 6's answers as well. Okay, if there are no doubts, we'll discuss the last week's problems. So it's continuation from week 5. Uh, which of the following is not the consequence of Kasha's principle? So Kasha's principle deals with Stokes shift, verosymmetry, as well as quantum yield of ignition. Singlet to triplet transition probably is negligible is not a uh, valid assumption because singlet to triplet transition helps you uh, calculate phosphorescence as well. So the answer is singlet option C. Singlet to triplet transition probability is negligible, which is not the consequence of Kasha's principle. Question number 8. For transition involving dash operator, the parity of initial and final states need to dash. So, uh, from the calculations of the parity operator, we were able to say that it's pretty straightforward. It's a MCQ. So, if the operators are odd, then they are opposite, and if the operators are even, then the parity is same. So both option A and B stand true. For radiative transition, the parity of the initial and final states need to be uh, opposite, same, cannot be determined, and cannot be determined for molecules with inversion symmetry. So here the correct option is option A, opposite. So for radiative transition, the parity of the initial and final states need to be opposite. And as a direct consequence of the ninth question, for transitions mediated by kinetic energy operator, the parity of the initial and final states need to be same. So the answer is option B. The last question for week 5. Phosphorescence occurs when the molecule undergoes transition from triplet to singlet state. Such transitions occur as a reflection of the fact that options are symmetry rules are not followed in real systems. Option B, state mixing. The excited state of the molecule is not a pure triplet but a mixture of triplet and singlet. Option C, non-radiative decay is faster from triplet than singlet. Option D, low quantum yield for fluorescence compared to phosphorescence. Out of these, for phosphorescence, the only option that yields is option B, which is state mixing. So the excited state is not a pure triplet but a mixture of triplet and singlet states. That's why your phosphorescence happens when the triplets singlet state to a triplet state transition happens. So that's all the questions for week 5. So next we'll go to week 6's question. So first question is uh, rate of stimulated emission dash. So uh, there are two options which say which say it's not dependent. There is one option that says it's not dependent on molecular characteristics, and there are two options which say it's dependent on molecular characteristics but is either are not modified or can be modified, and the fourth option says it can't be modulated. So stimulated emission, we know that it's dependent on molecular characteristics, and stimulated emission can also be modulated. That's why we have the quantum mechanical operator involving the energy state ek. So the correct option is option C. Stimulated emission is dependent on the molecular characteristics and it can be modulated. So question number 2. Given that a system has reached optical transparency, net change in the incident and emitted photons is zero, we can say that what? So optical transparency is a phenomenon where your uh, incident and change in the incident and emitted photons is zero. So the options given here are the rate of excitation is equal to uh, emission, stimulated emission, and the rate of excitation is equal to that of total rate of decay. There is no absorption of photons, and no molecules are undergoing transition. So out of these options, the correct option is B. That is, the rate of excitation is equal to that of total rate of all decay. So third question. If there exists a laser media system with the possibility of optically pumped 3 as well as 4 level lasing at a given laser wavelength, in this system what will happen? So compared to a 3 level system, the 4 level system, the threshold is very low. So energy, energy, energetically, with respect to kinetic energy, only the 4 level laser is preferred than a 3 level laser. So as a result, we will be only seeing the lasing corresponding to 4 level system. So the correct option will be here is option B. That is, we will only see lasing corresponding to our 4 level system. So next question is, uh, when is the 2 level laser possible? So we know that compared to a 3 level and 4 level laser, kinetically your 2 level laser is not possible because your population inversion won't happen. Population inversion won't happen naturally. So that population inversion has to be induced. So out of all the options saying that if it's optically pumped, it's not possible as the population inversion is never possible. And they are saying that last two options are saying the population is inverted using electrical or magnetic means. So if it is optically pumped, the population inversion will not be possible in a two level laser because the rate of decay will still be the rate of decay to a non-radiative state will still be more. So the only way the population is inverted if it is inverted using electrical or magnetic means. So the correct option is option C or option D. Option C as well as D. If the population is inverted using electrical and magnetic means. Uh, this is a continuation of the second question or the third question, I think. The order of thresholds in different lasing systems are as follows. So two level laser doesn't have any threshold per se. Only 3 level and 4 level systems have a laser threshold. Out of that, the 3 level laser has a higher threshold than the 4 level laser. That's why it's not preferable compared to a 4 level laser. So the correct answer here is 3 level greater than 4 level. Option B. So question number 6, the amount of energy needed to, uh, as same question almost. Uh, Start a 3 level laser is lesser than 4 level laser, but takes more time to reach steady state. Start a 4 level or 3 level laser is equal. Option C, start a 4 level laser is lesser than 3 level laser. Uh, Fourth option is start the laser depends on the laser cavity and not on the media. So it's a pretty straightforward question if you had answered all the previous questions. The answer is it's easier to start a 4 level laser than the 3 level laser. So because the amount of energy needed to start a 4 level laser is lesser than a 3 level laser. So question number 7, if the reflectivity of output coupler increases, what happens? So if the reflectivity of output coupler increases, the options given are threshold for lasing will come down, average output power will increase. Option B is the opposite, exact opposite of the first option with respect to a laser threshold, and option C and D are both threshold and average increases or decreases. Out of this, the correct answer will be that the threshold for lasing will come down and the average output power will increase, making it more easier to be making it more easier for the photons to be pumped to the higher level, making inversion population inversion very easier as a result. So if the inversion is more, your output power also will be uh, less because of more photons being excited, where the threshold will be coming down. So it's second, eighth one is a MSQ multiple select question where they are asking about the units of spectral brightness. So spectral brightness we know that it will be measured in both watt meter and watt per second. So the correct option will be power by option A, power by length, and option C, power into time. Sorry, watt per meter and watt second. The last two questions are pretty straightforward questions. The one ninth question says in an interferogram involving two beams as the coherent uh, in an interferogram involving two beams as the coherent length increases, what will happen? So the options here is option C, the uh, distance over which the constant parameter remains constant decreases. And the last question is, what is the test of coherence? So the test of coherence is interference as well as distribution of phase. Sorry, not distribution of phase, change in phase differences over space or time. So if there's no phase difference over space or time, then it means that it's coherent. And if it is interfering, constructively interfering, and all the destructive interferences are cancelled out, then it means that the laser beams are coherent. So that's all the problems that are given for uh, the discussions for week 5 as well as week 6. So till the end of the session, I'll have the doubt session. If any people have any doubts, they can shoot up. Else we will meet in the coming Sunday for the week 8 session, which will be on 15th March coming Sunday from 3 p.m. to 5 p.m. So if no one has any doubts, we'll meet again on next Sunday, just 15th March from 3 p.m. to 5 p.m. Thank you.